So this is the ninth session on Newton's laws of motion. This is in continuation of the eighth session. So in this also I'll take up some more numericals on Newton's laws of motion. Okay, some numericals on Newton's laws of motion will be taken up. Solving problems on Newton's laws of motion. Okay, so I'll write down the question first. A small block of mass m is initially at rest over a smooth horizontal surface. Smooth horizontal surface over which it is free to move. A time dependent force F equal to Bt square begins to act on the block at an angle of 30° with the horizontal as shown. Okay, now we have to find several things. Find first the time instant t naught at which the block just loses contact with the surface. T naught at which the block just loses contact with the surface. Second, speed of the block at the instant it breaks off with the surface. The speed of the block t equal to t naught. That is, at the instant it is just about to break from the surface and lose contact with the surface. And third, distance covered by the block till this instant. Distance covered by the block till this instant. Distance covered by the block till this instant. Okay. So these three things we have to determine. Okay. I draw the diagram here. Okay. So, solution is this. First, I draw the diagram of the situation. This is a smooth horizontal surface. This is the block of mass m, which is initially at rest over this surface. A force F barabar Bt square begins to act on the block, which makes an angle of 30° with the rightward horizontal as shown. This is the block at t equal to 0. Now, first it is said, at what time instant starting from initial moment will the block lose contact with the surface? See, why should the block lose contact with the surface? Because see, this force increases with time. B is a positive constant. As time passes by, force F goes on increasing in magnitude. So its vertical component F sin 30° that also increases in magnitude. At certain instant, Bt square sin 30° just becomes equal to mg. At that instant, normal force vanishes. And just infinitesimally small time later, the block loses contact with the surface, because then the upward component of Bt square just exceeds its weight, and then the block loses contact with the given surface. So, in first thing we have to find what time instant is the block just about to lose contact with the surface. So Suppose what I do, at arbitrary instant I draw the free body of this block. What forces act? mg, n and F equal to bt square. These are the only forces acting on the block, okay? The block just loses contact with the surface when upward component of F, that is bt square sine 30 degree, just balances the weight of the block. So at t equal to t naught, the block just loses contact with the surface, where t naught is the solution of the value of t as given by the equation. T naught, say at t equal to t naught, upward component of F, that is bt naught square sine 30 degree, is just equal to mg. So mg is equal to bt naught square sine of 30 degree. Okay. So mg is equal to bt naught square sine 30 degree. This is the instant at which normal force just vanishes. And just infinitesimally small time later, the block loses contact with the surface. Because then component of F in upward direction just exceeds the weight of the block. So from this we get mg equal to bt naught square by 2. Sine 30 degree becomes 1 by 2. So t naught becomes root under 2 mg by b. This is therefore the required answer. Okay. First answer has been obtained. Second thing, we have been asked to what is the speed of the block at the instant it loses contact with the surface. So what do we do till that instant? What do we do? See, in the time instant interval 0 to t naught, okay, the block is always in contact with the surface. So what do we do in this interval? We apply Newton's second law to the block along its line of motion, that is in the rightward direction. So suppose we take this direction to be x-axis, say. Okay. Now we apply Newton's second law to the block in positive x direction. So net force on the block in positive x direction is Fx, that is equals to Fx dash minus Fx double dash, that is equal to m times dv by dt, where v is the velocity of block at time t along x-axis, that is vx, which is just denoted by v itself, because vy and vz are 0. Fx dash is what? It is the sum of x components of real forces on the block, which makes positive angle with positive x-axis, that is simply f. So f cos 30 degree. So Fx dash becomes bt square. This just becomes how much? This becomes bt square cos 30 degree minus Fx double dash. What is Fx double dash? Sum of x components of real forces on the block which make obtuse angle with positive x-axis. There is no force which on the block which makes obtuse angle with positive x-axis. So this becomes 0. That is equals to m dv by dt. Okay. So this equation can be integrated easily with respect to time to obtain the answer. So we get m dv by dt barabar bt square root 3 by 2. Okay. So I shift dt right side. M dv becomes b root 3 by 2 into t square into dt. So I integrate this equation on both sides. M dv 0 to v, that is becomes b root 3 by 2 t square dt 0 to t naught. On integrating this last equation, we get mv is equal to b root 3 by 2 t square integrated between 0 to t naught gives t naught by 3. This becomes b naught by b by 2 root 3 and t naught cube. T naught cube becomes 2 mg by b power 3 by 2. So this is the answer to the so this means v becomes, I divide this by m, so this becomes b by 2m root 3, b by 2m root 3 into 2 mg root 3 by 2. This becomes 2 root 2 mg root mg by b root b. So this goes, oh sorry, This and this goes away, m also goes away. So from this we get the velocity of the block at the instant it just loses contact with the surface. So I rub this one here, okay, fine. So we get that at the instant it loses contact with the surface, its speed v is given as how much? This becomes c. This 2 also goes here, okay. So what do we get here? V becomes root 2. Then it becomes what? G root mg. Root 2 g root mg by root 3b. This is the answer to the second part of this given question, okay. So with the speed at the instant it breaks contact with the surface is g root 2 mg upon root 3 into root b. This is the answer to part B of the question, okay. Now we are asked to find the distance moved by the block till the instant it loses contact with the surface. See, this v is strictly speaking the velocity, okay. Now we have to find the distance covered by the block till the time instant it loses contact with the surface. See, in this entire time duration of motion between 0 to t naught, the block is moving along a straight line without in a fixed direction, an outward direction. This motion direction doesn't change. So in 0 to t naught, distance covered is numerically equal to magnitude of displacement. So simply if we integrate v with respect to time, we get the distance moved. So solve the third part of question. What do we do? We write ds by dt is equal to v. This v is the, not this v. This v is different from this v. This v is the speed at time t equal to t naught. And this is the v at arbitrary time lying between 0 to t naught. Okay. Now this v already we have determined from this equation. So now we have to find this v. Now this as I mentioned just now, it is just the v at time t. It's not v at time t naught, but it's the v at time t. Okay. So how do we find that v at time t? So in the part B of the question, we integrate to find v at time t naught. We integrated between the limits 0 to t naught. In case we want to find the velocity at time 0 t, instead of integrating from 0 to t naught, we should integrate from 0 to t. So I'll write down the equation once again. N dv by dt is equal to bt square cos 30 degree. So this becomes bt square root 3 by 2. Okay. Now shift dt that side. So m dv becomes bt square root 3 by 2 into dt. Alright, fine. So this side up, okay. So I integrate this equation from 0 to v and 0 to t. See, here we'll integrate from 0 to t, not from 0 to t naught. Because to find the distance moved, we have first to find the speed at arbitrary instant t, where t lies between 0 to t naught. So this one integration gives b, see t square is here, I'm sorry. T square is inside the integral, okay. So this becomes b root 3 by 2, t square dt 0 to t becomes t cube by 3. So what v we get at arbitrary instant? It becomes b root 3 by 6m into t cube. This is the v at arbitrary instant t, where t lies between 0 to t naught. Okay, fine. I rub this one. So what do we get here? So we get v is equal to, this v is also the speed, magnitude of velocity is speed. Speed can be written as ds by dt. This becomes v root 3 by 6m into t cube. Alright, fine. So I shift dt right sides. So ds becomes b root 3 by 6m into t cube into dt. Now to find the distance moved between 0 to t naught, we integrate both sides. 0 to s, b root 3 by 6m t cube dt 0 to t naught. This one integration gives what? S is equal to b root 3 by 6m is constant. So it comes outside the integral, and t cube dt 0 to t becomes 1 by 4 into t naught power 4 it becomes. And t naught is this quantity. This becomes b root 3 by 24m into t naught power 4. T naught square becomes how much? 2mg by b. Again this square it becomes how much? 4 m square g square by b square. Okay. So distance moved by the block in this time interval 0 to t naught is just equal to how much? It becomes this 4 goes away, m goes away. So b this becomes how much? Here m will go away. mg square root 3 mg square root 3 by 6 m 6b root this is answer. Okay, so s becomes how much? S becomes mg square root 3 upon 6b. This is therefore the required answer. Okay, this is the distance moved by the block in the time 0 to t naught when it just loses with contact with the surface. This is answer to part B of the given question. All right. So S becomes how much? S becomes this much. Okay, and t naught 4 becomes square of this. So it becomes 4m square g square b square. Okay, so it becomes mg square root 3 by 6b. This is therefore the required answer S. Okay, fine. All right. I rub this one. All right. I take up second question. Okay, on this video I take up second question on this video. So I'll write down the question here. Okay, I'll write down the question. Fine. See, it is given this problem on Iridov. Okay, it's a question from Iridov, problems of numerical problems in physics by I.E. Iridov. I'll write down the question. Okay, see, the question is this: a block of mass m is initially at rest. Over a smooth horizontal surface. And is free to move over the surface. Okay. Force of constant magnitude F. A force of constant magnitude. F equal to mg by 3 starts acting on this block. Begins to act on this block. It begins to act on this block in the course of straight line motion. Of the block, the angle theta between block and surface, angle theta between the rightward horizontal and force F depends on distance covered S as theta is equal to some C into S, where C is a positive constant. Okay, fine. Find the speed of block as a function of angle theta. Okay, this is therefore the required question. Alright, fine. This question is of field of. Okay, so what do we do first? I first draw the diagram. First draw the diagram before solving this problem. The diagram has to be drawn. See, this is a smooth horizontal surface. This is the block here, initially at rest. This is at time 0, this is initially at rest. So at time 0, theta is 0. So initially force F acts on it, F acts in rightward direction, constant magnitude mg by 3. Now as time passes by, magnitude of this force remains constant, but its direction begins to change in this way. At certain instant t, what happens? The block comes here. At this instant it is moving at F makes certain angle theta with the rightward horizontal, and block has gained a speed v. So I have to find v in terms of theta. Okay. So at this instant t, what I do? I draw the free body of this block, mg and n. Okay. F is in this direction, mg, and these are three real forces on the block. Now apply Newton's second law to block in this direction. Okay. So normal force is a right angle to this direction, has no component. Mg also has no component in this direction, right angle concept. Only component F along this is F cos theta. Suppose I take this motion to be along, say, x-axis. Apply Newton's second law to block along positive x-axis. So I write m dv by dt. See, its velocity vx is itself the velocity v. V is just the x component of its velocity. They are equal because it's undergoing a straight line motion. So m dv by dt is equal to net force in x direction, that is fx. That is equals to fx dash minus fx double dash. Now what is fx dash? Fx dash is the sum of x components of all the real forces on block which make acute angle with theta. That is simply f. So it becomes f. Fx dash becomes f. No, it becomes f cos theta. And f is mg by 3. So I write it as f cos theta. And what about this fx double dash? Fx double dash is the sum of x components of real forces on block which make obtuse angle with rightward x-axis. There is no force on block which makes obtuse angle with rightward x-axis. So fx double dash becomes 0. So now what I do, I apply chain rule. I write it as like this: dv by ds into ds by d theta into d theta by dt. That just becomes how much? F cos theta. Alright, fine. Now I rub this one. So I draw a line here. Okay. So what do we get? M dv by ds, that is will remain here. dv by ds into ds by d theta. ds by d theta. Now what is ds by d theta? Tell me. I'll write it here again. Okay. ds by d theta into d theta by dt. Okay. I'll just rectify it. Okay. Slightly just. I'll just write it chain rule here. dv by ds into ds by dt. I'll write it in this way. Okay. A small calculation I made. I've made a calculation error, so I'm just rectifying it. So this becomes m dv by ds into ds by dt. Okay. That is just equal to f cos theta. F is equal to mg by 3. Magnitude is constant into cos theta. Now you see m and m will go away. Okay. Now ds by dt becomes v. So this becomes how much? V dv by ds is equal to g by 3 into cos theta. Now theta is how much? Cs. So we write it as g by 3 into cos of Cs. Okay, so V dV becomes G by 3 cos of CS into ds. Now what I do, I integrate this equation on both sides within suitable limits. Okay, so this becomes G by 3 into cos of CS into ds. S limit becomes 0 to S. Initially when S was 0, block was at rest, and when S becomes S, its speed V becomes V. So this one integration and inserting limits, we get V square by 2 is equal to G by 3 comes outside the integral cos CS into ds, 0 to S. Okay. So what do we get here? We get V square by 2 is equal to G by 3C, and we integrate this, then C comes out here, denominator, and then we get sin CS, inserting limits, we get sin CS. But we have been asked to find V in terms of theta. Now CS is just equal to theta. So we get V square equal to 2G by 3C into sine of theta. Okay. So V becomes how much? V becomes root under 2G by 3C into sine of theta. This is the required speed V of the object in terms of distance angle theta. Fine. So this is the answer to the required question. Okay, fine. Alright. I love this one, okay. Now I take up a third question, okay. Third question I take up on this Newton's laws of motion. Fine. This question also belongs to Erudov question, okay. I'll write on the question. An aerostat of mass m. An aerostat, this is the book on Erudov, I write on the question. An aerostat of mass m starts coming down with a constant acceleration a. With a constant acceleration a. Determine the ballast mass to be dumped for so that the aerostat begins to move up at same constant acceleration a. At same constant acceleration a, and air drag is to be ignored. Air drag on the aerostat is to be ignored. Air drag means viscous force, resistance force on the aerostat due to the surrounding air. Air drag is to be ignored, alright. Only one more thing we have to assume, only weight and buoyant force acts on the aerostat. Is also given. Only weight and buoyant force acts on the aerostat. Okay. is therefore the required question. Okay. Now how to solve this question, that is the problem. First what we do, we draw the diagram. Okay. We draw the diagram first. Alright. First we draw the diagram. So I would say it is something like this. This is the big bucket. Okay. And by some mechanism this is a balloon. This is the balloon. Okay. And total mass of this is m. Initially it is moving downward at acceleration a. M is the mass. So in downward motion I draw the free body. mg, weight of the ballast, and this surrounding air exerts a buoyant force Fb, upward direction. Okay, fine. Now what I do, I remove some mass from the aerostat. Suppose I remove m1 mass. Mass of remaining becomes what? M minus m1. So see, this is a balloon, okay. I remove m1 mass, so mass becomes, weight becomes m minus m1 into g. It is being assumed that the buoyant force remains constant. Even though some mass from aerostat has been dumped, removed, still the buoyant force doesn't change. Okay, now it begins to move upward with same constant acceleration a. We have to determine the value of m1. m1 we have to determine, okay, fine. So what I do, I apply Newton's second law to the aerostat in downward direction. In this case, when mass was not removed, okay. So this one I write here. I apply Newton's second law to aerostat in downward direction. In downward direction, what is the net force? Mg minus Fb. Mg is F dash, Fb is F double dash. So we get Mg minus Fb is equal to Ma. Okay. This is the Newton's second law applied to the aerostat in downward direction when it was moving downward with acceleration A. Now what I do, I apply Newton's second law to aerostat in upward direction when after some mass has been removed, mass m1 has been removed. Still the buoyant force remains the same, okay. See, we are assuming that, one thing I would like to say, this buoyant force is nothing but V rho g. It is the volume enclosed by aerostat into density of air into g. So even though some mass has been removed from this bucket, the volume enclosed by the aerostat doesn't change. So buoyant force also remains same in both downward and upward journey of the aerostat. So now apply Newton's second law to aerostat in upward direction after some mass m1 has been removed from it. So what now? Fb becomes F dash in upward direction. Fb minus m minus m1g becomes F double dash. That is same as m minus m1 times a. Now what we do? We add these two equations, so Fb will get eliminated. First equation is this, second equation is this. Now first or second equation we add up, Fb goes away. And what do we get? Mg minus m minus m1 into g is equal to, adding these two terms, Ma plus Ma minus m1a. Alright. So this becomes Mg minus Mg. So it becomes Mg minus Mg plus m1g 2Ma minus m1a. So this term goes away. m1 comes this side. m1 into g plus a is just equal to 2Ma. Alright, fine. I love this one, okay? This one I love. So, on solving this, what m1 we get? m1 we get as 2Ma by g plus a. This is therefore the required answer. Alright. So m1 becomes how much? m1 becomes 2Ma by g plus a. Is therefore the required mass to be dumped from the aerostat so that it begins to move upward in same constant acceleration a in upward direction. Okay. This example also it finished. Okay. This was a 9th session on Newton's laws of motion. I took up these 3 problems to demonstrate the concepts. Okay. So in next session also I'll make more videos on Newton's laws of motion integration based problems. Okay. So this I close it here. Fine. Alright. Is it alright? So I close this here. Fine.